back to 6th grade science. So in the last video, I referenced that we're going to be spending a few more days on thermal energy. So here we are for thermal energy part 2. I know we've only talked about it like 67,000 times right now, but I want to remind you of what thermal energy is. Thermal energy is the energy of moving atoms in matter. More specifically, it's the total kinetic energy of moving particles within matter. Remember that all matter has thermal energy because particles are always moving. So, thermal energy transfer. What is it? Anyone remember? Maybe anybody? Am I talking to myself? I mean, technically, yes, I am talking to myself, but I'm pretending I'm talking to you in the audience at home. So, thermal energy transfer is when particles collide. Energy goes from the warmer particles to the cooler particles. These particle collisions continue to happen until you've reached an equilibrium where things are at equal temperatures and equal amounts of thermal energy. More specifically, there are 3 types of thermal energy transfer that we're going to be discussing today. And the first one is conduction. Conduction is the transfer of thermal energy between particles of matter that are touching. This usually occurs in solids and liquids faster than in gases because, hint, gases are good insulators. But don't worry about that right this second, we'll get into that later in the video. A lot of you are probably very familiar with conduction without realizing it. How many of you have ever baked cookies, or anything for that matter? I have. Conduction in an oven works with thermal radiation, which we'll get into later in the video, heating up the metal baking pan, or baking sheet, whatever you want to call it. The metal heats up quickly because it's a good thermal conductor. We'll also talk about that later in the video. So once the metal heats up, then it's touching the cookies or whatever it is that you have baking in the oven, and it causes it to cook through conduction because the warm baking sheet, baking pan, touches the item that you're baking and then cooks it. And then you also have cooking from thermal radiation, but specifically what I'm talking about right now is the cooking that's happening on the bottom of the cookies or whatever delicious treat that you're making. Other examples of conduction include ironing. When you iron your clothes, you have the cooler shirt and the hot iron. The hot iron is touching the shirt and heating it up through conduction. So in the end, your shirt is warmer than it was when you started. How many of you drink hot chocolate or tea or even coffee and you're holding the mug and it feels nice and warm in your hands? The warmth that you're feeling is from the thermal energy transfer from the hot beverage to your hands, which are colder, through conduction. The particles of the liquid are heating up whatever container you're holding, which is then in turn heating up your hands. So it goes conduction A and conduction B. Conduction A in this example is when the liquid is heating up whatever container it is in, whether it's a ceramic mug, paper mug, metal mug, whatever. And then conduction B is happening because it's transferring from whatever you're holding your drink in to your hands. So it goes from the hottest object warming the second object, which is then warming the third object. An electric stovetop is another example. A gas stovetop technically is, but that gets a little tricky, so we're not going to get into it. But with an electric stovetop, you have the pan of dinner that you're making for people at home, and you set it on top of the electric stovetop and then turn the electric stovetop on. The electric stovetop then heats up, which is touching the pan or whatever else you're cooking in. And from there, the stovetop heats the pan, which then heats the food. So again, you have a conduction A and conduction B. Conduction A occurs when the stovetop is touching the pan and heating it up, and conduction B occurs when the pan is hot and is then heating up the food. So you go from the hottest, heating up, to the second hottest, and then the third item, which is the coldest, and it heats in that order. Right now it's fall, and pretty soon it will be winter, which means that snow is coming. Snow is the last example that I want to talk about. In the other examples, I've talked about having a hotter item then transfer to a cooler item, but I'm going to talk about that just in a little bit of a reverse sense. When you pick up a snowball, it's cold. So instead of the snowball transferring thermal energy to your hand, It's the opposite. Your hand is going to transfer thermal energy to the snow, causing it to melt. Because remember, thermal energy is always transferred from a warmer object to a cooler object. The next type of thermal energy transfer that we're going to talk about is convection. Remember, conduction is when particles are touching. Convection is through a fluid. More specifically, convection is the transfer of thermal energy by particles moving through a fluid. Now, when you think fluid, your first thought is probably a liquid like water or something along those lines. But in this sense, fluid means either a liquid or a gas. A good example of convection is boiling water. When you first put the water on the stovetop and then start heating it up, the particles in the bottom get warmer quicker. So when that happens, they start moving faster and faster and faster and faster until eventually they move so quickly that they lose density, which means that instead of being like this, they're farther apart. When that happens, these rise to the top. And as they rise to the top, they're hitting and running into the cooler particles of the water at the top. So when they collide, what happens? Yes, when they collide, the thermal energy from the warmer particles transfers to the cooler particles. So what happens here is the thermal energy from the warmer particles dissipates, and eventually they lose, instead of as much speed as they have, they lose it and get slower and slower. When they get slower, their density starts to increase because they get closer and closer together. And when this happens, they circle back to the bottom. What's at the bottom? The heat source. So as they go down, they start to heat up again, and essentially it makes what's called a convection current, where you have your particles warming up at the bottom, going up to the top, cooling down, and then repeating. You're probably a lot more familiar with convection currents than you know, or at least know of yet. They happen all the time in nature, and we don't necessarily realize that that's what's happening. But you'll learn more about that in earth science in 3 years or so. The first example that I'm going to touch on with convection currents in nature is the molten rock below Earth's surface. It creates a convection current because it goes from down below, heating up, going up top, cooling down, and then just repeating. Another couple good examples are water in the ocean and then air in the atmosphere. Convection currents in the air work by the land being warmer during the day, which heats the air up, rises up, goes over some type of body of water, cools down, comes back down, and then repeats. At nighttime, the water is warmer than the land, so it goes the opposite. The air heats up over the water, rises, and then comes over land and cools down. Convection currents always work in this type of cycle. The final type of thermal energy transfer that we're going to talk about today is thermal radiation. So thermal radiation is what keeps life going on this planet. More specifically, the sun. We get heat from the sun through thermal radiation because thermal radiation is the only type of thermal energy transfer that can travel through both air and empty space. When the waves of thermal energy reach an object, it ends up heating up the object by transferring its energy to the object that it's touching. That's why when you're outside in the sun, it feels warm on your skin. Radiation is the only type of thermal energy transfer that doesn't need matter to happen. Another good example of thermal radiation is a campfire. When you are sitting around the campfire roasting s'mores, you feel the heat coming from it, and those heat waves that you feel is thermal radiation. So, what are some sources of thermal radiation in everyday life? Have you guys ever seen those infrared cameras that you look at things and they turn blue and green and red and yellow depending on what you're looking at? The hotter something is, the more red it seems. What you're looking at with those is thermal radiation. So going back to the question of what has thermal radiation? Everything, 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 even if it doesn't seem like it. Ice cubes give off thermal radiation. Now they're a lot cooler than you or I, but they're still giving off thermal radiation, just in less amounts, because they're cooler. All types of thermal energy transfer can work together. So an example is a campfire, like the one behind me. If I had a metal pot filled with water that I wanted to boil over the fire, I can hold it there. From the fire itself, heat is radiating, because I'm not touching the metal pot to the fire, I'm just holding it over it. So you have thermal radiation from the fire heating the bottom of the pot. When you're heating the bottom of the pot, then you get inside the convection currents, because the bottom of the pot is then heating the water through conduction to create the convection currents, because the water is going from warm to cool, back to warm, and so on and so forth. So besides that little example of conduction that I whispered to you there, another example of conduction in this is the metal pot itself. So have you ever been working on a stovetop and holding a handle of a metal pan, and sometimes it gets really hot? That's conduction. So in this example, when I'm holding my pot of water over the fire, the handle gets warm, and from there heats up, feels hot in my hand, and that's conduction. Up next, we're going to talk about thermal conductors. So I just popped up out of a toaster. Why would I do that? Because I want to talk about thermal conductors, which I've touched on a little bit earlier. Thermal conductors are materials that are good at conducting thermal energy, which means moving it. Metals are very good thermal conductors because they have free moving electrons, which allows energy to transfer quickly. But that still doesn't answer the question of why I popped out of a toaster. How many of you have ever made toast or something in the toaster, and you look inside and see those coils that get really red hot? Are good examples of a thermal conductor. Because I said earlier that metal is a good thermal conductor, that's what they're made out of. So those items get hot very quickly, which in turn toast whatever it is that you're toasting. So just like we have thermal conductors, we also have thermal insulators. Thermal insulators are materials that are poor thermal conductors. So good examples of this are gases. Because the particles in gases are spread so far apart, they don't often collide. Even when they're moving around really quickly, they're more apt to collide, but they don't always do it. So they don't transfer thermal energy well, because remember, to transfer thermal energy, the particles have to collide. So what does this mean? It means that the heat of the particles is retained for longer, because if the particles aren't colliding, then they're not transferring their thermal energy, which means they're holding it for longer, which means they have more heat. Have you ever seen insulation at a home improvement store or even in the side of your house? It's oftentimes pink or yellow or different colors. Insulation works by trapping air inside, and assuming it's hot air because you're heating your house, it's going to help keep the heat in your house longer, rather than the air going through your wall out into the world and heating the world. It stays within your house and continues to heat your house, because those particles aren't able to transfer their thermal energy as quickly as other things. Plastic and wood are other good examples of insulators because they don't transfer the thermal energy as quickly as liquids or other solids like metals. So this brings our talking of thermal energy to a close for now. Remember, science builds on each other, so there's always a chance that we're going to visit it again. If you guys have any questions, please remember to reach out to your teacher, whether that's Miss Cameron or myself. Bye!